Welcome. This is the Cisco CCNA ENSA, also known as the Enterprise Networking Security and Automation course. This course focuses on the CCNA version 7 curriculum. This is course 3 of 3. So moving on, how do we modify a single area OSPF? So let's look at the metric that OSPF uses. OSPF uses a cost metric, and the cost will be the reference bandwidth divided by the interface bandwidth. The default reference bandwidth is 10 to the 8 power, or 100 million. Therefore, the formula should be 100 million bits per second divided by the interface bandwidth in bits per second. So because the OSPF cost value has to be an integer, things like fast Ethernet, gig, and 10 gig share the same cost. So you can actually modify this by doing an auto cost reference bandwidth so that we can get different values. And what I mean by that is, because again, fast Ethernet, gig, 10 gig, they're all set to 1, even though realistically they are not the same. So by doing the adjustment, we can get the appropriate bandwidth. And again, the cost value has to be an integer, so if we actually do this, we should not be getting 1 for everything. 0.1 is 1. 0.001 is still 1. So that's one of the reasons why that cost analysis, or that cost adjustment. To assist OSPF in making the correct path determinations, the reference bandwidth must be changed to a higher value to accommodate the faster networks. So anything faster than 100 megs. Again, in reality, 100 megs used to be fast, 20 years ago. It's no longer the same, so adjustments had to have been made. So by changing the reference bandwidth, it does not actually affect the bandwidth capacity. To adjust the reference bandwidth, we could use the auto cost reference bandwidth in megabits per second router command. So we can actually set a 10 gig link by doing an auto cost reference bandwidth 1000. If we want, that would be our gig. If we wanted 10 gig, it would be 10,000. To return to the default, we would set it back to 100. 100 is again just 100 megs. Another option to change the cost on one specific interface is using the IPOSPF cost command. So we can adjust that. So how does the reference bandwidth chart look now when we've actually modified it? So now we're looking at when we see 10 gig, cost would be 1, gig would be 10, a 100 megabit would be a cost of 100. That way we have more an appropriate cost so that OSPF can use the appropriate cost values to actually do the forwarding. The cost for OSPF routes should be an accumulative total between them. So if we want to go from here to the internet, it would be cost 1, cost 10, and over. If we want to go route 1 to route 3 to route 2, it'd be cost 1, cost 10, cost 10 again, and to the internet. So here would be a cost of 20, here would be a cost of just 10. The lower the cost, the better. So this would be the preferred path for this connection. This would not. However, if these were 10 gig links and this was just a gig link, then the preferred path would actually be R1 to R3, R3 to R2, R2 to the internet. But that's assuming these were 10 gig links and the costs were adjusted. So how do we see that as a number? So again, here we have 1 plus 10, that cost total is 11. This cost would be 1 plus 10 plus 10 internet. So this would be 21. So verifying the accumulated cost for a path, you could actually look at a IP route and you could see the cost or the metric used. So again, we have a metric of 11 because we have the cost to go from this PC to the router, from the router to router 2, and so that'd be 1 plus this cost of 10. That's how we get that 11. The lower the metric, the better. So reasons to manually set cost value is if you actually want to control the flow of traffic through the network. Connections to the equipment from other vendors could also be an issue, or if they're using different routing protocols. So test failover to a backup route. We can always verify by adjusting the cost of one route to verify that a backup route actually kicks in. And you'll notice here we have our backup route values. You'll notice the metrics are higher. So let's talk about our hello packet intervals. OSPFv2 uses hello packets, and again they're transmitted to a multicast address 224.0.0.5. That's all OSPF routers, and this is done every 10 seconds. You can modify the default timer if you wish. The hello packets are not sent on passive interfaces, typically the LAN. So, yeah. The dead interval is the period of time that the router will wait to receive a hello packet before declaring the neighbor down. If the dead interval does expire before the route receives a hello packet, then the OSPF will remove the neighbor from its database. The router will flood the database update to all of its neighbors. Cisco will use a default of 4 times the hello packet interval. So if the router does not receive a hello packet from its neighbor within 4 times the normal hello interval, then it will declare it's dead. So Cisco uses the default of 4 times for the hello interval. This is basically 40 seconds on a multi-access or point-to-point network. So how do we verify hello and dead intervals? If we do a show IP OSPF interface, we can look at the timer intervals. We can look at the hello, the dead, the wait, the retransmit, and the resync numbers. In the CCNA, we're mainly focused on the hello and dead timers only. So we can also do a show IP OSPF neighbor, and you can see the dead timer. And again, by default, this value is refreshed every 10 seconds. When the router receives a hello packet from the neighbor, it will refresh the dead timer. So how do we modify the intervals? Underneath the interfaces, we could do an IP OSPF hello interval and the number, or a dead interval and the number. You can also then remove them by doing the no IP OSPF hello or dead interval command, and that would reset them back to their default values. In this example, we've modified them to 5 seconds and 20 seconds. And again, the dead timer has to expire in order for the routes to be classified as dead. We have a packet tracer lab modifying these values to verify retention of that information. So going on, we have section 2.5, the default route propagation. This is basically how to propagate a default route from one router to everyone else. So if we have a default route, for example, we set a IP route for 000, 000, we send it out loopback 1. How do we propagate that route to everyone else? In OSPF, we have a command called default information originate. That will allow us the propagation of the default routes. Again, IP route should be quad zeros, space quad zeros. the next hop or the exit interface. If we issue the default information originate command, this will instruct the other routers to be the source of the default route. So if we have 3 routers and router 2 says, I have a default route to the internets, I can propagate that route to my neighbors, to router 1 and router 3, by using the default information originate. And we have a lab doing this. So how do we verify the propagation? You should see on R2 would be a static star. Star denotes a default route. S denotes a static route. Here we have a OSPF learned E2. And this is just a clever way of saying that this is a OSPF learned static route that's a default route and how to send it. And this is sent to router 2. E1 and E2 is beyond the scope of this module because again this is a higher level routing concept, but for our understanding it's again just basically stating send to router 2 because router 2 is propagating that default route. We do have a lab covering default route propagation. 2.6 is about verifying single area OSPFv2 and a review of those show commands. Again, show IP OSPF, show IP OSPF neighbor, protocols, and interface. These will all give us very specific information that we need to understand when we're looking at and troubleshooting OSPF. So again, show IP OSPF neighbor will verify the router has formed adjacencies, and it will give us our router IDs, it will give us our states, it will give us our dead times, and it will give us our addresses. And if we have priorities set, it would give us those as well. If 2 routers may not form an adjacency, again, it could be wrong subnet, it could be mismatch hello and dead timers, maybe the network types don't match, or incorrect OSPF network commands. So we need to be able to understand how to fix those. So doing things like show IP protocols, that will give us things like our routing protocol ID, it will give us our router ID, it will give us our interfaces, and it will also let us know if those interfaces are in an area or not receiving hello packets because you might have accidentally set them as passive. So those are all good reasons to use the show IP protocols command. If we are looking at show IP OSPF, that gives us again our OSPF, our process ID, our router ID, it will give us our area 0, and it will give us how long our algorithm has been functioning, and it will give us our reference bandwidth and things of that nature. Though this is more in depth, and this is actually outside the scope of the CCNA. Show IP OSPF interface will show us our process ID, our router IDs, our network types, our cost, and the adjacencies that we have formed. If we want to just do a quick overview, we could do a show IP OSPF interface brief, and that will show us our interfaces, our process IDs, our areas, our addresses, our costs, our states, our neighbors as well. And you'll notice the chart is not always lining up correctly because of spacing, but this will be our costs, this will be our state, and this will be our neighbors. And that is it for this module. If you got any questions or concerns, please reach out. Thank you.